Today, I'd like to talk about linked lists, though I recognize that you probably don't want to use linked lists in Go. And the reason for that is because modern computers take advantage of spatial and temporal locality. That is, we tend to access memory in sequential order and usually around the same time. Therefore, caching and prefetching speeds up memory operations quite a bit. Whereas using linked lists that utilize pointers into non-sequential memory locations subvert or kind of like circumvent the efficiency you get out of sequential memory access. And that's probably why Go uses slices as its kind of primary sort of list data structure. But the reason I'm talking about linked lists today is because I think the way we typically learn linked lists, like in college, or like your first algorithms class, does us a bit of a disservice. It spares students of having to understand pointers to pointers because it's a bit of like a mind bender in exchange for exposing us to edge cases that occur when appending, prepending, and particularly deleting from a linked list. There are plenty of Go linked list tutorials on YouTube, and so I encourage you to stop right now and search YouTube for Go linked list tutorials. Watch them and familiarize yourself with how they do them. And I think I'll be able to show you a different way to do it that is simpler, ultimately. So go ahead, I'll wait. Okay, so now that you know what linked lists are and how they're typically implemented, I'm going to show you how I would do it in Go. So we're going to start by making a package called list. And we're going to create a module. I'll probably put this on GitHub, so we can say go mod init on github.com ang64 list. Now we could just make our list.go, call it package list. And so typically you have like a node type, something like type node, which is a struct, and then you'll have a value, some value of some type, and then a next, which will be a pointer to node. But since it's 2026 and we have type parameters now, we can make this list generic. So we could say node type t, which could be any type, and thus our v, our value, can be of any type. And our next will be a pointer to a node of that type. All right, so far my package isn't, or my editor isn't showing any errors. So now that we have our linked list node, we could start implementing the operations that we perform on lists. The three operations that I will probably write are like prepend, append, and maybe delete. So let's start with prepend. I think that'll be the easiest one to do. And again, remember what I'll be doing is passing a pointer to that node. If you remember what you saw in those other videos, typically they just pass a pointer to that node. So let's start with prepend. So func prepend with our type parameter of t, that could be anything, and we'll pass it maybe our node, which could be, or which is a pointer to a pointer of node type t, and then we'll have a value of type t. And it doesn't return anything because this will always work. And so really prepend is super simple, right? Since we have a pointer to our node, we know that it won't be nil because we've passed the address of some pointer. And that pointer, of which the address we've passed to this function may point to nil, but we don't care because we're going to modify that pointer in place. And the easiest way to prepend is to say the current pointer points to a new node that has a new value, with its next value being that of the previous node. I'm not sure if I explained that well. I think I can write it better than I can explain it. So here it is. We could say what n points to is a new node of type t with its value of v and its next being n. Okay. And that's it. We don't care whether or not n is nil. That's not a special case. That means that the zero value for a pointer to node is completely usable and perfectly valid value to pass to prepend. And I can demonstrate that. Let's test, right? So let's edit list test.go, maybe say package list, and create a func test prepend t testing t. I'll get all this boilerplate out of the way. All right, so I'm using like the very latest version of Go, and I think Go Please doesn't like it. So I'm gonna have to quit and edit this again. Testing still isn't being loaded. Oh well. Anyway, what we can do now is create a list value, maybe events. So we'll say maybe var L is of type node int, and prepend we'll pass the address of L, so a pointer to a pointer, and we'll pass it maybe 1 and some other kind of pseudo random values, right? Like 12, 42, maybe -8, 128, and 13. There you go. And so since I'm prepending, what I expect to see is that if I walk this list from head to tail, I'll see these values in reverse order, or at least in reverse to the order that I prepended them in. So the next thing I'd like to do is build a small loop where I iterate over our nodes and just like print the value to the terminal. So maybe for we'll just reuse L. So as long as L doesn't equal nil, as long as L doesn't equal nil and L equals L next, let's t.log f the value of L.v. And so if I go, well, we still don't have our imports set up. I'm not sure why. There we go. All right, so now if we say go test run verbose, okay, so we see our list in reverse order, right? 13, -128, etc., all the way down to 1. But notice that prepend is just one line. We don't care whether or not n is nil or anything because it'll never be nil. I mean, I'm sure you can kind of coerce it into being nil, but if you pass it the address of a pointer, then by the very nature of having to pass it the address of some variable, it'll never be nil. So let's move on to append, which just means that we have to walk to the end of the list, similar to the way we printed the list in test prepend. We just have to walk to the end of the list, find the address of the last next node, and modify the address of that last next node in place. The neat thing about appending is that the 0 value, again, or nil node will work just fine. So we could say func L append, because append is already a keyword. Our node T and the V, or our value V. And I'll just, again, reuse n that's on the stack and say for n not equal nil, we'll say n equals the address of n dot next. And so the reason I have to parenthesize star n is because the star doesn't bind closely to n. So without the parentheses, right, I'd be asking for the address of next. I'm sorry, I'd be asking to dereference n dot next, whereas I just want to dereference n to get its next value and then get the address of its next value. But really, I don't need to do anything in the body of the loop, because all I'm doing is moving n to the end of the list. And so at this point, all I have to do is modify n in place, and it's going to look very similar to prepend. And so all I have to do is say n equals node with a v, value of v. And I don't need to give it a next because the 0 value for next is going to be appropriate, right? We want it to be nil. And so now, hopefully if this works, we only have 3 lines to append, and we don't care about whether or not we're passing in a nil. So there's no like special cases. So let's go back to this. We're going to yank everything from line 5 to line 19. So 5, 19, yank, and then paste. And we're going to test L append. I'm going to change everything between line 24 and line 30 to L append. Okay. And then likewise, we're going to print the list again. So we're going to test. And as you can see now in the output for test L append, we're printing the lists in the sequential order, or at least in the sequence that we appended it in, right? So we have 1, 2, 12. Whoops. All right, so now I'd like to delete from our list. And if you recall from the other videos you watched, delete is like a little bit weird because you typically have to walk the list until you find a next value that has the item you're looking for, and then you could sort of like rearrange some pointers using the next value. And it's a special case that if your list is nil, that you just ignore it, right? But in this case, we could say func delete L delete T any our root node, type T, the value you want to delete. And we're going to need some sort of like comparison, comparator, or whatever, compare function that tells us whether or not we found the node that needs to be deleted. So we'll just say like comp is a func that takes type T and type T and returns bool. And essentially it'll return true if T and T are equal, and of course false if they're not. And again, this function doesn't return anything because we're doing all of our modification in place. Again, we simply want to walk the list until it either equals nil or until we find the value that we want to delete. So as we walk the list, now we actually have to like do something in the bottom of the list. We could say like if we compare what n points to's value with the value that we passed in. And this is actually wrong, right? We want to, again, like I said before, we want to kind of make sure that the asterisk binds with our pointer to a pointer and not with the member of that struct, right? Actually, what I want to do is say if they don't match, let's continue, right? And then keep our happy path to the left. And so now that we've found the node, now that we found the address of the next value that contains the value that we want to remove, that was a mouthful. All we have to do is change it to the value of the next value of that node. That's a mouthful, but when I type it, hopefully it'll make sense, right? So now all we have to do is say n equals the address of n. The address of what n points to's next value. I think that's it. And then return. And that'll effectively, what are we worrying about? Value n is unused. This value of n is never used. So n equals the address. Oh, excuse me, I'm sorry. What n points to equals n.next. Sorry, excuse me. I confused myself there. And maybe that's why people don't implement linked lists like this, maybe. So let's test our delete function. I'm just going to reuse our prepend. I'm going to reuse append. Yeah. So lines 19 to 33. We'll yank those and paste them and say test L delete. So here we just append some values to it. And then we could try deleting something from the middle, right? So maybe say delete, L delete from our list 42. That should yank one right out of the center of it. And we'll give a comparison function, maybe a type int that returns bool, and this function simply returns if a equals b. And so now when I test, hopefully 42 is removed. Yes. So as you can see in the test L delete output, 42 is yanked right out of the middle. So the special cases for delete in or the special cases for deleting a node in a singly linked list, well, one obvious one is if you take out the first one, right? So let's try removing 1. And as you can see, 1 was yanked out without needing to even ask whether or not we're dealing with the first or dealing with a nil node or not. Another tricky case might be deleting the last one. So let's try doing L delete on 13, our unlucky node. And of course, it deletes that just fine without having to treat it as a special case. And so that's it, really, for the most part, which, again, I'd like to point out that by using a pointer to a pointer of our node and modifying like our root or our head node and the next nodes in place, we eliminate several special cases. If you go back to those other videos on implementing linked lists, those special cases should be pretty apparent. Maybe just like a little bit of icing on top. Something I'd probably do with this package is maybe add an iterator. So maybe something like func all, all with t any. And in this case, we don't have to pass a pointer to a pointer. We could just say n is a pointer to a node of type t, and it'll return a iter seek. Let's see if go please picks that up. No. All right, so I'm gonna quit again. There we go. So now we could just return a func that takes another function called yield that accepts a value of type t that returns a bool. I know that's a mouthful, right? And I'm going to repurpose one of these loops. I'll just take this one. So again, we don't have to like create a new value. We'll just recycle our node from the stack. But in this case, we don't have to dereference it. We could just do that. And now we could just say if yield, if not yield, excuse me, n.v. That is, if like the loop of the range function, or if the body of the range breaks or returns or anything like that, we'll return ourselves. Return. Oh, I'm sorry. We have to supply the type parameter to seek. That's probably why iter didn't pick it up. I mean, probably why go please didn't pick it up. So I'm not going to pick on go please today. So let's try that out. Again, let's repurpose test lappend. So we're going to yank lines 19 to 33. Paste it here and say test all. And now instead of having to construct our own loop that has to be aware of keeping track of the state of L, we should be able to just say for v equals range of all of L. And this is complaining. Declared and not used v. Oh, that's because we could say that because we're using v, not L. Right. So for v equals range over all of L, let's just log v. right? So now when we run go test, run everything, verbose, test all, prints everything. So that's it for today. I'll probably expand on this using other data types. And so again, what I hope this serves as is a foundation for the next video, which will probably be on binary trees, which I'll probably then extend to balanced binary trees. Because again, hopefully you can imagine how this could be useful when dealing with binary trees, because a lot of the operations at the end of the day are very similar. Clearly you might have like a wrapper type here, like maybe, so list, you might have like a list head, right? That is of type any. It's another struct that contains a head. It contains a head node, which is a pointer to a node of type T, and maybe like a length of type int, right? And then you might have like methods associated with it that manage it, right? So maybe like append, and then some value of T, right? And you can kind of hide some details about how, and also a comparator, right? So you can maybe store comp here, and that would be a func of T that returns a bool, right? And so now like append could simply be, L append H, or the address of H.nv. And likewise, and then, might say hlen plus plus. And likewise, prepend could be prepend, and then again, you increase len. I guess delete might be a little bit trickier, because you want to know whether or not anything was deleted. I'll leave that as an exercise. It's not my intention to like fully flesh this out. But my point is, in order to provide like a nice interface, I'm sorry, this should be pointers. In order to provide like a nice API around lists, you might want to add methods to kind of like an enclosing function. an enclosing type. But that's all. That's all I have for today. And now that you've gotten to the end, if you care, I'd like to explain why I'm doing this. I recognize that we typically don't need to implement linked lists and other kind of fundamental data structures. I find that I spend most of my time using Claude or some other AI assistant to code. I still consider writing code a creative endeavor. You get to choose your own abstractions, name things, and I still want to exercise those things that I enjoy about coding. And so this is my opportunity. I hope those of you who are kind of experiencing the same thing try to find some kind of fun out of writing hobby projects without AI. Because I think it's important to maintain our fluency in particular languages, right? Like something I pride myself in is that I could typically kind of like riff and go without having to look up anything. And I find that that's becoming a rarer and rarer skill. And I also find that if I don't exercise that skill, it atrophies. So that's it. My next video will probably be on trees, maybe balanced trees, maybe heaps, maybe other fundamental data types, and I'll see where to go from there. Thanks.